Alright, so the last part of 9.1 will be all about the applications of vectors. Basically, a fancy way of saying word problems. Um, you guys should have, by now, after going through 9.1 A and B, have all the tools necessary to handle basic vectors. And the idea is simple. Vectors are these quantities that have a size, a magnitude at a particular direction. And if that's all the information you have, it's sort of hard to do mathy stuff with them. But in 9.1b, we learned that vectors can be decomposed into their components. And when you have vectors in component form, it's very easy to do math stuff with them because all you have to do is do the math, adding and subtracting on the individual components. So, like with everything in mathematics, when it comes to word problems, I hate to say it, there's no one-stop formula that allows you to do it. It just takes practice, it takes intuition, it takes mathematical thinking. So this is going to be sort of a double-edged sword video. I mean, it's going to be a simple video, but at the same time, this concept will either be easy or hard depending on how good we are with word problems. And again, the only way we can get better at it is with practice. So all I did was I just picked three random examples just to, do with you guys because I honestly believe that one way to develop good methodology, good technique is just to see a whole bunch of solutions done and try to adopt that thought process, try to adopt those techniques into your own planning. So throughout these examples, I'm going to interject some of the things I'm thinking about, interject some tips and suggestions, so on and so forth. So without further ado, let's just dive into some word problems because again, there's nothing new to teach in terms of technique per se. It's just seeing these solutions in action. I pre-typed out the word problems, so at any time I would suggest you pause the video so you can completely copy down the problems in your own notes. But I'm just gonna dive right on in. So this question says we have an airplane that heads due north at 300 miles per hour. It experiences a 40-mile per hour crosswind flowing in the direction of north 30 degrees east. So we have some bearings again. Express the velocity v of the airplane relative to the air and the velocity u of the wind in component form. Part B, find the true velocity of the airplane as a vector. And part C, find the true speed and direction of the airplane. Now, for those guys who might not understand what's going on here, is that velocity is a very stereotypical application of vectors because it is an amount, 300 miles per hour, 40 miles per hour, but also the direction in which that speed is going is sort of important. So that's why we can join those two together as this quantity called a vector. Now, even if you don't have to be a pilot, but you should know that speeds, when they intermingle with each other, they affect each other. Um, if you've ever gone swimming in a pool or in the ocean, or if you've ever gone walked on those moving sidewalks at the airport, you should know that when you're going at a certain speed, and the environment around you has its own certain speed, it will either speed you up or slow you down. And that's exactly what's happening in this situation here. Now, I'm going to do a quick sketch here, not a great one. You don't need to copy this down because I'm going to erase it. But you have an airplane that's going due north, and then you have a crosswind that's going north 30 degrees east. So north 30 degrees east is up and to the right. So if the air was perfectly still, if you're flying an airplane straight up, you expect to go straight up. But because we have this wind here going at a particular angle, I hope everyone understands. I mean, heck, just throw a leaf in the air when it's windy outside, you'll see that leaf moving side to side, like be pushed by the air. So with this airplane going due north and the wind affecting it to the top and to the right, we expect that the airplane is going to go at a slight angle, and that's exactly what this question is asking us to do. Eventually, it broke it down into three parts for us. So let's go ahead and solve this problem. Let's do the first part. So part A, it says express the velocity of the airplane relative to the air and the velocity u of the wind in component form. It's basically asking us to break down these velocities in component form because believe it or not, they did give us magnitude and direction. So this is what we did in 9.1b. Here's a magnitude and direction, find the component form. So let's dissect all the information that they gave us. And I'll put them in two categories, airplane and the wind. So if I reread the problem, it tells me the airplane heads due north at 300 miles per hour. So I hope everyone can agree that that is an amount. If you ask the question, how fast is the airplane moving, and someone said 300 miles per hour, that is an amount that they told us. So they actually gave us the magnitude of the airplane, which the problem said use v, as 300 miles per hour. Now, you saw my sketch. Even though it didn't explicitly say it, it did implicitly tell us the angle or the direction of the airplane. It says the direction heads due north. So if you were to sketch that out, due north, north, south, east, west, due north is up here. So the angle, I can just know by visualization, I'll call it theta v, is 90 degrees, or pi has radians. I'm going to go ahead and use degrees just because that's what the problem used. The problem used degrees here, and typically when it comes to word problems, I tend to use degrees because it's easy to visualize. If it wasn't a word problem, I would use radians, but because it's a word problem, we'll use degrees. Let's go ahead and do the same thing for the wind. So what information does it tell us? It tells us that the wind is going 40 miles per hour, so that's its magnitude, that's its speed. So they said use W or use U for wind. And it goes in the direction of north 30 degrees east, which is a bearing. But we have to remember, when it comes to math with vectors, it needs to be a direction measured from standard position, measured from the x-axis. So although this is a perfectly fine way of describing direction, north 30 degrees east, we need to measure it from standard position. So again, here's north, here's east. Refresh your memories from unit, what was it, unit 6? Yeah, I think we did bearings in unit 6. From north, you go 30 degrees eastward. So that's north 30 degrees east, which means his vector direction, doing quick math, what is that, 60? 6 degrees. Right. So theta u of the wind is 60 degrees. Then we should have everything we need to write these vectors in component form. So recall from yesterday that if you have the magnitude and direction, that the x component is going to be the magnitude. Should I write this? Yeah, I guess I'll write it out to show my work. Is the magnitude cosine of the angle, and the y direction or component is the magnitude times the sine of the angle. So that's it. So that's all we're going to have to do. So the x component of v is 300 cosine of 90 degrees. The y component of v is 300 sine of 90 degrees. Cosine of 90 degrees is 0, so that's going to give me 0. Sine of 90 degrees is 1, so that's 300. So all this work tells me that vector v in component form, you can do whatever format you want, the angled bracket, the I and J notation, or the stack column notation. I'm going to use the angled bracket notation, is 0, 300. And that's what we expected. The problem says that the airplane is going due north, so we expect all of the speed to be in the vertical direction, due north, and none of the speed in the horizontal direction. So let's rinse and repeat for the wind. So I'm not going to bother rewriting the formulas. So we know that the horizontal component of the wind is the magnitude cosine of the angle. The vertical component, the y component of the wind, is the magnitude sine of the angle. And then these guys are special unit circle angles, so we shouldn't need a calculator. Cosine of 60 degrees is 1/2, so this will give me 20. And sine of 60 degrees is rad 3 over 2, so it's 20 rad 3. So there we have it. So the velocity of the airplane is this guy, and the velocity of the wind is 20, 20 radical 3. So those are the velocities in component form. So that's part A. Right? Hopefully you have the original problem written on your page. I guess I shouldn't do a line. It's part of the same problem. Because I'm going to be scrolling up and down here. So it says find the true velocity of the airplane. Now, as a vector, when you hear this phrase, I guess this is something I need uh, to tell you. You can't do this problem if you don't know what true velocity is. When you hear that phrase, true velocity, that means the resultant vector. That means add the velocities. So the airplane itself might be going 300 miles per hour due north, but if you were to put this airplane in the crosswind it's expecting, it's not going to end up flying 300 miles per hour due north. The engine on the airplane, the speedometer might read 300 miles per hour due north, but with the wind, it's actually going to affect the overall velocity. So that's what the term true velocity really means. Just find the sum of the velocities. Just find the overall velocity when you factor in the airplane and the wind. Well, that's just a fancy way of saying resultant vector. In other words, add the velocities, add the vectors. Well, in part A, we found the vectors in component form. This was the whole concept of yesterday. Adding velocities or adding vectors in component form is really easy. You just, well, add the components. So the true velocity is simply v plus u. That's it. That's all you got to do. So we're going to go ahead and just add them. Add the x's components and add the y components. So we have 0 plus 20. I guess I should highlight this. 0 plus 20 for the x. So that's going to be 20, comma, and 300 plus 20 rad 3s for the y. 300, because they're not like terms, I'm going to leave them separate like that. Now, since it is a word problem, it's okay to get decimal approximations. So I'm going to break out my calculator, and we get 20, comma, 300 plus 20 rad 3. That's approximately 334.64. So that's the true velocity of the airplane. So although it is going 300 miles per hour due north, if it's in this wind, it's going to go slightly faster in the vertical direction, because this is bigger than 300, but it's also going to tilt a little bit to the right, as we sort of expect. If you have an object going north and something's pushing it up and to the right, it's going to end up going faster up, but slightly to the right. And then let's scroll up. Part C says find the true speed and direction of the airplane. When you hear the term speed, right, the word true I've already explained above, but the term speed is magnitude of velocity. That is the scientific definition of speed. Speed is basically velocity if you ignore the direction. So at any of the time these word problems ask you to find speed, that's just code word for magnitude of velocity. And I hope I don't need to explain what direction is. That's pretty self-explanatory. So since they want true speed, well, we already have the velocity in component form. This is 9.1b. Given component form, can you find the magnitude? So true speed is simply the magnitude formula. X squared plus y squared. 334.64 squared. Since that's going to be an ugly number, you're just going to get a decimal approximation. So type that into your calculator, you're going to get a decimal approximation of about 335.2 miles per hour. So that's the true speed. Now for the direction, it's the same formula as yesterday. Tangent of theta is y over x. So in this case here, tangent of theta is, now I'm going to go ahead and use the exact version. So just to make things as accurate as possible, I'm going to use this version here, just because I can, instead of the decimal approximation. If you use the decimal approximation, you're just going to be off a little bit. So y over x. So I'm going to take out my calculator and use inverse tangent. So if you use inverse tangent in degree mode, because the whole problem was in degrees, I'm going to get approximately 86.6 degrees. So that's the direction. Now, a little word of advice. I like to give my answers in the same format that the problem was given. Notice how the the directions were given in bearings, so I'm just going to go the extra mile and make sure that my answer's in bearings as well. Let's do a quick refresher on what bearings are. So the first thing I'm going to do is I'm going to visualize what 86.6 degrees is. So that's about 86.6 degrees. You have to remember that compass bearings always start at north or south. Very obvious question. You can see that this angle is closer to north than it is south. And then once you figure that designation, you ask yourself, is the angle leaning towards east or west? So we can clearly see that this angle is going up and to the right, so it's going to be north and east. So from north, we have to figure out what this angle is. And hopefully that's going to be a simple math problem, 90 minus 86.6. So that's going to give you 3.4 degrees. So that's the direction. So true speed we found up here. And then we can see that the direction in compass bearings is north, 3.4 degrees east. So if you're doing these problems and you're finding the direction and you check the answer key and it's not matching, just try compass bearings. They probably did compass bearings. Right? So again, the skills involved are the same skills we've been doing in 9.1 and 9.1a and 9.1b. We did, breaking things down into component form. That's what we did yesterday. Adding vectors in component form. That's what we did yesterday. Finding magnitudes and direction. This is all 9.1b work. Just you're applying it in the context of a word problem. So please don't let the word problem scare you. The only way you can get better at it is if you do a lot of them. I did prepare another example. So let's take a look at this example here. Again, feel free to pause the video if you want to copy this down, but I'm just going to go ahead and dive right into the problem. It says, a woman launches a boat from one shore of a straight river and wants to land at a point directly on the opposite shore. If the speed of the boat relative to the water is 10 miles per hour and the river is flowing east at a rate of 5 miles per hour, in what direction should she head the boat in order to arrive at the desired landing point? Let's just try to see what this is, what this looks like. So we have a river here, and it's very sneaky. It actually tells you the direction of the river. The river is flowing east, so I know this is not an up and down river, right? If I were to sketch this river, water's flowing, this would be a bad picture because this is an up and down river. If the water's flowing eastwards, this has to be a left to right river. So actually, hey, I can actually make straight lines here. Try to be somewhat pretty and accurate. So here's our river that flows left to right. And a woman is on one side of the shore. So here, let's just say this is where she is. Now she wants to go straight opposite, go straight to the opposite side of the shore. So this is what we want. So I'll call that W for wanting. However, we do know that this river is flowing, right? So I guess I should use arrows instead of wiggles. We know that the river is flowing in this direction. It says it flows east at 5 miles per hour. So again, even though you never sailed a boat, you should know that if you're going in this direction, but you have something pushing you to the right, you're not going to go straight. You're going to be going at an angle. So what the question is asking you is, how much does she have to compensate in order to reach to this point here? Now I hope everyone understands logically that if you have a river flowing to the right and you want to end up going perfectly straight, that you have to compensate by going a little bit to the left. So this, let's just call this our v velocity. I'll use the same notation as the previous problem. And let's draw in our water vector. So we know that the water is going straight east, and I think the previous problem used u. So that is the picture of this problem. We are looking for v in order to end up with w. So that's what the question is asking. Let's highlight the question. The question says, in what direction should she head the boat in order to arrive at the desired landing point? So I don't know how to tackle this problem. There's no set formula for this. So let's just go ahead and write down a true statement that we know. we know contextually, according to this problem, we know that whatever velocity that the woman is traveling in, when we add it to the velocity of the water, it should equal the overall velocity that we want. So that's exactly what we're going to write. We know the W velocity should equal the woman's velocity plus the water's velocity. So let's go ahead and set up that equation, right? We can't solve a problem without writing an equation first. We know that this is vector addition, and vector addition is easiest when things are in a component form. So let's go ahead and write the component forms of V and U. Well, I hope U is pretty easy to see. Do you see how it's going? It's laying flat, so the angle is 0. It is going perfectly east, so its entire speed is in the horizontal direction. And it told us the speed of the water is 5 miles per hour. So I shouldn't have to do any math. I hope everyone can see that vector U, that 5 is all in the horizontal direction and it has nothing in the vertical direction. It's a velocity v that's going to be a problem because it has a variable. It tells us that the woman is rowing 10 miles per hour. So I know that the magnitude, this whole length there, is 10. But it doesn't give us a direction. As a matter of fact, that's what we're trying to solve for. So that's our theta. Right? So for the woman at least, in the x direction, it's the magnitude cosine of the direction. Again, we don't know what the direction is, so we'll keep it as a variable. And the y is going to be the magnitude sine of the direction. So for the woman at least, we know it's going to be 10 cosine theta, comma, 10 sine theta. So now we can set up our equation. We know that our overall vector would be the sum of these two vectors. So we'll go ahead and add it. X plus x, comma, y plus y. Now, 0 plus that is just, anything plus 0 doesn't change. So this would be 10 sine theta. So that's great. We have this, but how does that really help us? Well, let's take a look at what we want. We overall want this guy here. And do you notice how it is perfectly vertical? Now, we should know something about the component form of vectors that are perfectly vertical or perfectly horizontal. That's what makes horizontal and vertical vectors special. We know that perfectly horizontal and vertical vectors, one component will always be 0. So that's sort of like the trick or the idea with this problem. So the idea that you need to know is horizontal vectors will always look like something, comma, 0, and vertical vectors will always look like 0, comma, number, because that's the definition of horizontal and definition of vertical. Definition of horizontal, you're not going up and down. Up and down is 0. Perfectly vertical, you're not going left to right. Left to right is 0. Well, we do know, according to the problem, that we want our overall velocity to be perfectly vertical because she wants to go across the river exactly straight across. Well, if I know, according to our drawing, if we want our overall vector to be perfectly vertical, that means we want our overall vectors horizontal to be 0. And that is an equation I can write down. We can write down, therefore, 5 plus 10 cosine of theta, we want that to be 0. And then, hey, what do you know? This is a trig equation. This is unit 7. We can go ahead and solve it. So get cosine theta by itself. Let's subtract the 5 and divide out the 10. So that gives us cosine of theta equals negative 1/2. So I'm going to do a reference angle here. So ignore the negative. What angle has a sine value of 1/2? Or excuse me, cosine value of 1/2? And 1/2 is special, so you should know that. That's 60 degrees. Now I got to place them in the right quadrants. And how do I know what quadrant we're in? We'll just look at the picture. Clearly, if the river's flowing to the east, we want to go up and to the left. So I know that my direction, my angle, has to be in the second quadrant. So if my reference angle is in the second quadrant, what is your actual direction? Your actual angle is 120 degrees. So there we go. So the direction she needs to row is a 120 degrees from the horizontal. So that's a pretty fun, neat problem. Again, the skills-wise isn't too complicated. You had solving trig equations, you had breaking down component form. I suppose you did need to know this, so this is something new to learn, but I think it's a very easy concept to convince yourself. Again, the only way you can get better at these is if you practice. I think I prepared one more example. I mean, at any time in this video, I'm not holding your feet to the fire. If you feel like you got it, you got it. But, you know, feel free to watch the whole thing or end early. I'm not going to know. But this is the last one I pre-prepared. And, of course, in class, you can always ask me for more questions, and I'll do as many examples as you need. This one here, they gave you a diagram. It says two forces F1 and F2 with magnitudes 10 and 20 pounds respectively act on an object at point P as shown in the figure. Find the resultant force acting on P. Remember the term resultant force. That just means add up the vectors. If you don't know what this term means respectively, that means that any numbers that they give you, they go in the set order. So notice how they said F1 first and F2 second. So that means these numbers go in order. So the F1, the 10 goes with the F1, and the 20 goes with the F2. So they gave us the magnitude, so we don't have to guess there. So F2 is 20, F1 is 10. Now, since it says find the resultant force, it means add up the vectors. As we said in 9.1b, adding vectors is easiest if things are in component form. So the very first thing we're going to do, or I should do, is rewrite everything in component form. So let's just go ahead and do the components. F1x is the magnitude. So what's the magnitude of F1? They told us was 10. Cosine of the angle. So let's take a look at the picture. Oh, that's nice. They gave us the direction. They gave us the angle. So that's just 45 degrees. F1y is magnitude sine of the angle. 45 is special, so we should be able to figure that out. So that's what, radical 2 over 2, so it's 5 rad 2s. So F1 in component form is 5 rad 2s, 5 rad 2s. That's not going to be our answer, but I'm going to start, so I can save it. Let's do the same thing for F2. F2 in the x direction is magnitude, which they told us was 20, cosine of the angle, and again, we don't have to figure it out. They gave us the angle in standard position, which is what these formulas always use. So that's 150 degrees. F2y is magnitude sine of 150 degrees. And again, 150 is special, so you should be able to figure that out. So reference angle 30, second quadrant. That's, what is that going to be? That's going to be negative, because it's in the second quadrant, 10 rad 3s. And this is going to be positive 10. Right. So all this work says the second force is negative 10 rad 3, comma 10. So what we have done here is we've written the components of the forces acting upon this point. So if I want to find what is the overall force that this point experiences, you just simply add up the vectors. Well, since it's already in component form, that should be a cakewalk. So what is the overall force? What is the resultant force? You just add up the vectors. So x plus x, that's 5 rad 2 plus negative 10 rad 3, comma, y plus y. 5 rad 2 plus 10. And, since this is a real-life word problems, it's okay to get decimal approximations. So pop that into your calculator. You're going to get approximately negative 10, comma, 17. Let's round to the nearest integer. And you can sort of see that in the picture. Even if you didn't have numbers, we can sort of draw it out because they gave us a picture. Remember, that's to add and subtract vectors. It's this parallelogram idea. So if we take this vector and put it at the end here, Or if we take this vector and put it at the end here, we can see that the resultant vector should be somewhat going up and to the left. So the x should be negative, the y should be positive, and that's exactly what we get here, negative x, positive y. Right, so those are just 3 random examples I found in the textbook. I'm not saying that every single problem you're going to see involves these contexts. Honestly, as always, in order to get better at word problems, you just have to practice. So have at it, give it a shot, and as always, I'll be here to help you whenever you need it.